On January 22, 2026, Earth, the Sun, and Threeey Atlas aligned at an astonishingly precise angle of 0.69 degrees, creating a rare celestial event that gave astronomers a once-in-a-lifetime opportunity to witness something of immense cosmic significance. This near-perfect alignment offered a fleeting window to gather unprecedented data on an interstellar object whose origin and nature have sparked both intrigue and skepticism. As sunlight bounced off the object's dust, creating what is known as the opposition surge, it became a unique chance to delve deeper into the object's structure and composition. The story of Threeey Atlas began on July 1, 2025, when the Atlas Survey Telescope, located in the Chilean Andes, flagged an unusual dot in the constellation Sagittarius. This dot wasn't just a distant star, it was an object traveling toward our solar system at an astounding speed of 61 kilometers per second. The discovery immediately turned heads. But what truly set Threeey Atlas apart wasn't merely its velocity, it was its trajectory, which would send it hurtling through our solar system on a path that no comet from our system could have possibly followed. With an interstellar origin, Threeey Atlas was on a one-way trip. Its hyperbolic trajectory meant it wouldn't return to the Sun, but instead would continue its journey out of the solar system, never to return. This wasn't just another comet from the outer reaches of our system, it was the third interstellar object ever detected, marking an extraordinary moment in astronomical history. The discovery was groundbreaking, not only because of its origin, but also because of the unusual characteristics it exhibited. What began as a routine observation quickly turned into a full-scale investigation. Early on, astronomers recognized that Threeey Atlas wasn't behaving like other comets. Its trajectory was unlike anything they had seen before. It was headed almost directly through the solar system's ecliptic plane, a path so close to the plane of our solar system that the odds of it happening by chance were vanishingly small, less than 2 in 1,000. The unusual alignment immediately raised eyebrows, leading scientists to question whether this was just a fluke or if something deeper was at play. Further observations revealed even more strange behavior. The spin axis of the object was also aligned in an unusual way, pointing nearly directly toward the Sun. This configuration, when combined with its trajectory, brought the probability of such an alignment to less than 1 in 10,000. These figures didn't just suggest an oddity, they pointed to something far more extraordinary. Threeey Atlas's dust trail, or antitail, also raised alarms. Unlike typical comets, which exhibit a dust tail that stretches away from the Sun, Threeey Atlas exhibited a sunward antitail, a 400,000-kilometer arc of dust that pointed directly towards the Sun. This unusual behavior further distinguished it from the rest of the comets cataloged by astronomers. And that wasn't all. In January 2026, Hubble's observations of Threeey Atlas revealed another surprise. The object appeared to have a triple jet structure, with one of the jets directed straight toward the Sun. Such a feature, never before seen in other comets, added to the growing list of anomalies that demanded closer scrutiny. The object's unusual behavior wasn't just a result of its interstellar journey. It suggested there was something fundamentally different about Threeey Atlas. Spectroscopic analysis of the comet revealed yet another puzzle piece. The ratio of nickel to iron in the object was extreme, and its coma, the cloud of gas and dust surrounding the nucleus, was dominated by carbon dioxide, up to 95%. Such a composition was far from the norm for comets in our solar system, whose comas typically contain water ice, carbon monoxide, and other gases. These extreme chemical features pointed to a possible origin in a very different environment, one that could have shaped the object in ways we didn't yet understand. As the data mounted, one astronomer, Avi Loeb, stood out for his unorthodox interpretation of the findings. Known for challenging mainstream theories, Loeb argued that the extraordinary alignments of Threeey Atlas could not be explained by random chance. The odds of the object aligning so precisely with the solar system's ecliptic plane, coupled with its spin axis pointing almost directly toward the Sun, were so slim, about 1 in 4 billion, that Loeb suggested that something beyond ordinary cometary behavior might be at work. Loeb proposed that the statistical improbability of these alignments indicated that the object might not simply be a comet shaped by natural processes. Could it be something more? Loeb speculated that Threeey Atlas might be an artifact of extraterrestrial origin, perhaps a piece of advanced technology from another star system, with its bizarre trajectory and unusual features suggesting an engineered object rather than a naturally occurring one. However, Loeb's hypothesis was not without controversy. Critics from the scientific community quickly pointed out that Loeb's calculations didn't fully account for observational biases or the limitations of current telescope capabilities. For example, telescopes like Atlas are more likely to detect objects near the ecliptic plane because this is where their search patterns are densest and detection is easier. This bias, they argued, inflated the apparent rarity of such alignments and made the phenomenon seem even more extraordinary than it might actually be. Other astronomers suggested that Loeb was stacking probabilities in a way that assumed each anomaly was independent, failing to consider that these features might all stem from similar processes of formation and ejection. These critics argued that such alignments, while rare, could occur naturally in the vastness of space. After all, in a universe as expansive as ours, even the most improbable events can happen. Despite the growing debate, NASA remained firm in its position. The agency continued to describe Threeey Atlas as a comet, one shaped by a unique environment far beyond our solar system, but still a natural object. NASA emphasized that while Threeey Atlas displayed extraordinary features, there was no evidence of any artificial origin. There were no technosignatures, no signals, and no indication that this object was anything other than a comet that had taken a very long, solitary journey across interstellar space. However, not every institution shared NASA's openness. In December 2025, John Greenwald Jr., a well-known advocate for government transparency, filed a request with the CIA for records related to Threeey Atlas. The agency's response was less than forthcoming, issuing a GLOMAR response, a refusal to confirm or deny the existence of any related records. This only fueled speculation among those who already questioned the official narratives surrounding Threeey Atlas. Why would such information be classified, especially regarding what appeared to be just another comet? In addition to institutional astronomers, amateur astronomers played a significant role in the ongoing investigation. Using smaller telescopes, these backyard stargazers captured remarkable images of Threeey Atlas, some of which rivaled the clarity of professional images taken by major observatories much closer to the object. These images, widely circulated online, raised further questions about the accessibility and transparency of data. Was the public being given the full picture, or were there gaps in the information that institutions were withholding? This growing divide between publicly available data and institutional control only added to the sense of mystery surrounding Threeey Atlas. While some scientists championed transparency, others warned that it was essential to be cautious in interpreting the data, especially given the object's extraordinary nature. The alignment on January 22, 2026 was far more than just a visually striking celestial event. It represented a rare, almost unprecedented opportunity to study Threeey Atlas in a manner that had never before been possible, allowing astronomers to gather detailed insights into its composition, structure, and perhaps its very origin. The key to unlocking this data lay in the opposition surge, a phenomenon that occurs when an object, in this case Threeey Atlas, is positioned precisely between the Sun and Earth. This alignment causes the sunlight to reflect almost directly off the object's surface and surrounding dust particles, creating a significant increase in brightness. The surge, in essence, acted as a cosmic magnifying glass, providing astronomers with a unique chance to examine Threeey Atlas with a level of detail that would otherwise be impossible. The primary focus of these observations was to better understand the structure of the comet's dust grains. These particles, which form the coma and tail of a comet, can reveal a great deal about its history and its formation process. Cometary dust is a valuable snapshot of the early solar system, with some grains possibly dating back to the birth of the Sun and the planets. By studying the grains' characteristics, whether they were loose and fluffy or more compact and processed, scientists could gain insights into the conditions that shaped them. Loose, fluffy grains suggest that the material is relatively unaltered, perhaps indicative of a comet that formed in a colder, less active region of space, untouched by heat or radiation. In contrast, compact and processed grains may indicate a comet that has undergone significant transformation, whether through thermal processes, exposure to radiation, or interactions with other cosmic bodies. These observations were particularly important because they provided a unique glimpse into the environment in which Threeey Atlas formed. Unlike comets that originated in our own solar system, Threeey Atlas was an interstellar traveler, ejected from a distant star system and journeying through space for billions of years before reaching our neighborhood solar system. Understanding the structure of its dust grains could help scientists piece together the conditions of its birth environment. Were these conditions similar to those of the early solar system, or did they differ in significant ways? Were the grains shaped by radiation from other stars, or had they been altered by the extreme environments of interstellar space? The answers to these questions could not only shed light on Threeey Atlas's own history, but also offer clues about the broader processes that govern the formation of interstellar objects. As astronomers closely examined the brightness curve created by the opposition surge, they compared it to benchmarks established by previous missions that had studied comets up close. One of the most important comparisons was with the Rosetta mission's study of comet 67P Churyumov-Gerasimenko. During Rosetta's rendezvous with 67P, the spacecraft observed a range of features in the comet's surface and tail, including varying degrees of dust grain size and composition. This dataset became a benchmark for understanding cometary dust. A broad opposition surge, like the one observed on 67P, would typically indicate that the dust grains were relatively unaltered and had a more porous, loosely packed structure. This would suggest that the object had remained largely unchanged since its formation, having never passed close enough to a star to undergo significant heating or processing. On the other hand, a narrow and steep brightness spike would indicate that the grains were more compact and dense, possibly the result of significant processing. Such a feature would suggest that Threeey Atlas had undergone a different kind of evolutionary history, perhaps having been exposed to higher levels of radiation, heating, or other environmental forces during its long journey through space. The nature of these grains could offer important clues about the object's exposure to different cosmic environments. For example, a steep brightness spike could imply that the comet had passed through dense regions of interstellar space where radiation and cosmic rays could have affected the dust grains. This could provide evidence for more extreme processes at play in its distant journey compared to other, more familiar comets within our solar system. After its close encounter with Earth, Threeey Atlas continued its journey toward the outer reaches of the solar system. On March 16, 2026, it would make a flyby of Jupiter, passing just 53.6 million kilometers from the gas giant. This flyby would be one of the last opportunities to observe the object up close before it returned to interstellar space. With a probability of just 1 in 25,000 for such a close pass, the scientific community is preparing for a final data collection blitz. Europa Clipper, JUICE, Juno, Hubble, and even the James Webb Space Telescope are all gearing up to capture any data they can before Threeey Atlas slips away into the vastness of space. Despite the lack of a dedicated probe or interception mission, this Jupiter flyby represents the last best chance for direct observation of this interstellar traveler. As Threeey Atlas continues its journey, the questions surrounding it grow ever more pressing. Where did it come from? What triggered its unusual trajectory? What secrets might still be hidden within its structure and composition? While NASA and other institutions continue to investigate, the answers may be elusive, and the mystery of Threeey Atlas may persist for years to come. For now, astronomers will continue to observe, speculate, and analyze this incredible object, with the hope that one day we will fully understand the nature of this interstellar visitor. But even as the official narrative unfolds, it's clear that Threeey Atlas has sparked a larger conversation about the possibilities of the unknown, reminding us all that in the vast, uncharted expanse of space, even the most improbable occurrences may be only the beginning of greater discoveries to come.